let's not waste our time. So any doubts, guys, from the last sessions, what we have gone through? Any doubts regarding the IP addressing, or have you tried going through it and understood something? Anything new anyone has learned to add on?
Yes, I have few doubts regarding what is the maximum size of MSS? Can we negotiate the changes? Like, can we negotiate the size of MSS?
Yes, you can. You can manually do that, or the TCP IP stack will do it for you. So that depends on the load which you are carrying along with the headers, right? So in the session, I have told you that MSS is related to segments, right? So this segment is nothing but the data which we are carrying, the actual data which is actually required, which the end user will be able to comprehend or understand. It's not the data along with the headers, right? So to answer your question, yes, we can negotiate, and also we can reduce this particular size. So I have told you a value, the maximum segment size. So that is around 1460 bytes. And why
Okay.
is that? Let me just
Okay,
present.
I have a small doubt again. Is there any default MSS value for the computer to choose this for a particular packet, for any packet to check? Not 1460, or is there any size or a maximum value for MSS?
Right, yeah, that is the maximum value. 1460 is the maximum value. There is no change in that. Let me just.
And you have told about jumbo frames as well, right?
Yes.
It is fixed size, and it make the size may also can change. And moreover, more computer, more like Amazon, Google, Microsoft. These people are using using big servers, like big frames.
Mhm.
And what is the maximum value of them all as well?
So regarding the jumbo frames, the maximum payload what they can carry is about 9,000 bytes. So that is what is that is why it is called as a jumbo frame. Now that is the maximum value for the jumbo frame. Just a second. Yeah, let me present my screen. Uh, right. Okay. So your question is regarding MTU max, MSS max. So the max in the sense the maximum value, and jumbo frame, the max value. So, in the previous sessions, I have told you the maximum values of each and every uh, transmission unit what we have got. So, in general sense, what we have is 1500 bytes is the maximum carrying capacity of the cables what we have got at home or in the normal organizations. And the devices like switches and routers, these are connected via these cables only, which has the maximum transmission unit of 1500 bytes, right? Now, before we discuss MSS, I'll tell you what is jumbo frame. So in jumbo frame, what happens is the maximum payload what it can carry. Now, what do I mean by payload? Basically, payload is nothing but the headers and the data, right? So if you see, this is the header here. So this is one header here, which is, let's say, TCP. Okay, and then we have IP header, which is this. Now this whole this whole data packet along with the headers is called as payload, right? So it is carrying this much. Now when it comes to jumbo frame, the maximum payload what it can carry, what that particular frame can carry. Now what is frame in here? Frame is nothing but the whole thing here, what we have, the payload. So this particular thing, how much it can carry along with the headers, along with the headers it can carry 9,000 bytes of data. 9,000 bytes of data. It's not bits, it is bytes, right? One byte is equals to 8 bits. This should be by heart by every one of you. You should understand that one byte is equals to 8 bits. Now this 9,000 bytes of data is nothing but the maximum value of the jumbo frame. That is why it is called as jumbo frame, right? And the maximum transmission unit what we have got in the general context is 1500 bytes, right? Is this clear?
Yes, sir. You told about TCP header plus IP header plus data. Is the data raw data or chunked data? You mean segment?
No, that depends. See, if I am having a TCP header here, right, and an IP header here and data here, this data can be the complete data or it could be the chunked data or
So
the.
we can call the payload as IP packet also, right?
Yes, you can call it as no, no. If there is a TCP header and an IP header along with the data, this is not called an IP packet then. If I would have drawn a diagram where this TCP header was not there, then you could have called it that okay, this is the IP packet, right? So now you can call this one as TCP IP packet because it is showing you the TCP header and also the IP header, right? Now, regarding the complete data and chunk data, don't get confused with this. Whatever headers we have, so as I explained you earlier, let's say we have a complete data.
Yes, sir. Got it, sir. Got it.
Yeah, so we just divide the data here, and each data will be added with TCP and IP headers. Each data will have that. And once this whole divided data reaches the end host, that data according to this IP and TCP headers will be reassembled into the comprehend in an understanding way so that the other end user can comprehend what data was sent. And this is possible using the IP header checksum value based on which you can do error free transmission. That is why it is important for us to understand the IP header. And in TCP header also we have the similar functionality of acknowledgements to see if there are any uh, packet drops in between, and if there are any packet drops then the same packet will be retransmitted back to the end user, right? So this is what it is. Now let us
Sir,
come to, yeah.
one more doubt, sir. In just you have told TCP, right? In
Mhm.
TCP, we have segmentation,
Right.
and uh, this is very small doubt for me. Is segmentation and segment both are same or different?
No, segmentation is the process, and after the segmentation process, whatever bits and pieces you have got of the data, of the whole data, whatever bits and pieces you have got like this, these bits and pieces are called as segments,
Okay, raw data which
which is
break into
divided.
pieces called segmentation.
That is called as segments. The data which is divided and is assigned. So these individual data is segment 1, segment 2, segment 3, and the process of dividing this data from the whole data is called as segmentation, right?
Okay.
The process is segmentation. After segmentation, whatever bits and pieces you are getting of that data, whatever divided data is there, those individual bits of data is called as segments. Segment 1, segment 2, segment 3. In a similar fashion regarding IP, if you fragment or you do fragmentation, that is the process, the fragmentation process, after that, whatever data you are getting, after dividing the packet, dividing the whole raw data into different packets, individual packets, these are called as fragments. Fragment 1, fragment 2, and fragment 3.
Got it, sir.
Right? Good. Okay, so now let's come back to MSS, the maximum value we have got. So remember, MSS is nothing but, yeah. So MSS is nothing but the actual payload data here, whatever data we are carrying. So the total length of that particular data, so the actual bytes of information what these IP and TCP headers are carrying is called as MSS, right? So in that context, the simplest way of calculating that is from your MTU. Let me type this just a minute. Okay. So from your MTU, you will be subtracting the TCP header size, the TCP header size. I'm not talking the total length or the total size of that particular packet, right? And from that, you will be removing the IP header size, okay? And whatever amount you are getting here, whatever value you will be getting here, that is the MSS. So in similar fashion for jumbo frames as well, when the researchers or the network administrators try to configure some frames in their organizations for jumbo frames, what they do is they decide what is the maximum value they will be using for the IP and the IP header, and what is the maximum value they will be using for TCP header. After subtracting that, that is the amount of data what this MSS, what this particular jumbo frame can carry, right? So it's not much of a data. This info, these IP and TCP headers are informational packets. These are not actual data. These informational packets are carrying the actual data. That actual data is called as MSS.
But TCP header and IP header are used as tags, right? Here,
Sorry, what was that?
uh, headers are used as tags. Can
uh,
we say like TCP header and IP header are used as tags to to send data?
yes, you can understand in your way as well. Yeah, what you can do is you can basically understand TCP and IP header as the address of the packet. So you are just attaching the address. Let's say you are sending a parcel or an envelope to your friend, right? What you do, you attach from and to address, right? So that from and to address here, whatever extra information you have added, that added data is the headers. What we are adding to each and every data packet. Because without these informational headers, this data is of no use. This data doesn't know where to go. That is how the routers will understand. So to clear that doubt, let me just explain you one short thing. So let's say this router is there. There is another router here, and there is another router here, right? So now, since we are all aware now that what is TCP header, what is IP header, and everything, we are aware of that as of now. So let's assume that we are sending some 1460 bytes of data. So that's the maximum data what I can send when I am using the normal frame, not the jumbo frame. So the MT will be 1500 bytes. From that, I will be removing 20 bytes of TCP header and 20 bytes of IP header, and the value will be 1460 bytes. So let's assume I'm sending this bytes of data. Now this data will be encapsulated with the IP header and with the TCP header, right? Okay, let's not confuse. So because we are now going from the network layer, so the 1460 bytes of data will be encapsulated. This data is in the application layer. That is why TCP will be the one which is encapsulating it. And then the IP will be the one which will be encapsulating it. Above that, whatever data link layer header is there, that will come here. And up above that, the Ethernet layer will add its own header. So for now, remove these two things from the context. We will just discuss about IP and TCP as of now, right? So now, this is how your OSI model also is. So this is the application layer, this is your transport layer, and this is your network layer. Now what happens? Now the packet, whatever this whole payload we have got here, this has to go from this 1.1.1.1 to 1.1.1.2 and 1.1.1.3, right? So it has to reach from here to here. Okay, so it has to go like this, but it will not go directly because there should be a medium how it will go. So the network is designed in such a way that each and every adjacent routers are aware who are their neighbors. So for this router is aware that my neighbor is 1.1.1.1 and from here my neighbor is 2. So because it is connected together with a single link. Okay, so I'm just making it simple. This is now actually how it works, but I'm just making it simple. From here, it is connected to this. So this particular router is aware that my neighbors are, this is this particular router which is hosted on 1.1.1.3 and 1.1.1.1. These two are my neighbors. So this router is aware of that. Now, so when we are sending the data from here, we will add the TCP IP stack of your device will add IP source as this particular router and the destination as this particular router, right? So now what happens is this 1460 bytes of data is going along with the 20 bytes of informational IP header and 20 bytes of informational TCP header, right? So now what is happening? So let's say the packet comes from here to here. The packet is still same because it is still in the network layer only. Okay. And then the packet from here goes to this particular destination and it reaches the network device of the end user who is connected over a laptop or something. Let's assume he is connected to a desktop PC. Now, what happens? The IP's job is done here. The IP's job is done here. So the packet came here. Now it is routed internally towards this particular device. And here comes the job of TCP header. The TCP header, what it does, it decides where shall this particular byte of information go. Because IP's job is to send the packet from one address to another address. But TCP's job is to send the packet to the exact TCP port, right? To the exact TCP port. Remember in the beginning class, I told you, whatever data we are sending, let's assume we are sending an email, right? And that email is using IMAP or POP3 protocol, right? So these protocols have their own TCP ports, which your system is aware of. That is the reason why the TCP ports are ranging from 0 to 1296, I think. I'm not sure about this number, but this 0 to 1296 are the reserved ports on your TCP IP stack. Okay, nobody can change this, nobody can modify this, no one has the authority to change it. The moment your device is built, the moment it is manufactured in the factory, in within the factory itself, these settings are there within your network interface card. Okay, now 0 to 1296, these particular ports, TCP ports, you cannot modify. Now IMAP is something which is on 110 port, right? Now, when the packet has come here, it sees from your TCP header, whatever TCP header this end user attached, this particular end user attached that 110 port, the packet should be destined to. Now, when the packet reaches this particular destination, it sees your TCP IP stack recognizes, okay, The packet has to go to 110 port. Let us open it or process it according to the email protocol, that is IMAP. And whenever you open your Outlook, your Gmail or something, the email will be visible to you without any issues. So this is how the IP and TCP header play a major role. So IP's job is to logically route these packets from one destination to another, right, through the network. So this through the network is across the globe. You might be sitting here in India, but you are able to communicate with the person who is in United States. How? It is because of this network cable which is laid within the sea, through the sea. Let me just show you that cable. Just a second. I'll show you that sea cable. Where is this? So there is a submarine cable map which is obviously available for free. Let me show you how many network cables are connected from one place to another. Okay, so I have it. I'll just share my screen. Okay, okay, you are able to see the screen.
Yes,
Hello.
sir.
So this is the map. This is your global map. What through which I am scrolling, and you can see these lines here. The lines which are in different colors, and they are connected from one continent to another continent, right? So no matter how much infrastructure you have, how much wireless infrastructure you have, at the end of the day, these sea cables are these sea cables actually play a very major role in sending your data packets from one location to another location. So if you see in India itself, how many sea cables are there? Let's see how many sea cables are connected from Mumbai, India, and from which other state is it? It's in Kochi, and then in Trivandrum and Tuticorin. From there, it is connected to Sri Lanka, right? That is how we are able to communicate with Sri Lanka. Now, the communication within the continent is happening by with the help of internet service providers. Let's say we have Tata, BSNL, ACT, right? These are all private companies, but BSNL is the only major player within India who actually provides the internet services. ACT, Tata, and all the other private players purchase the internet service line from the government, and they utilize that and provide the services to all of the customers. So, you and me, as in customers, right? The mobile data, what we use, it uses the satellite technology, yes, but that also is somehow connected within the sea cable infrastructure only, right? At the end of the day, it has to reach the packet, the data what you are trying to send from your mobile phone. It reaches to the local mobile tower. From there it reaches to the place from where it has to be routed. So at the end of the day, it will come back to the submarine cable only, right? So that is the reason why these all submarine cables are heavily guarded by each and every country. So there is a basic protocol and how we have to guard this particular sea cables, right? So you can basically visit this URL if you are trusted. I'll just share that in the chat. So you can visit this URL later, and you can definitely check it out a little bit in depth, because there is a lot of thing here, so you can explore at your end. But this is how actually the internet works. It's nothing like it is completely wireless, and we don't have the until now we don't have the capability of sending the data without these wires, without these network cables. However, recently people are starting to use satellite connectivity, but I don't think so that is going to come into the near future. It will take a little time, but currently this is how it is. And you can make a note of this particular URL because it is useful. It is useful because in interviews you might be posed a question how internet is working throughout the globe, across the globe. Is it wireless or is it in a wired format?
Who
Okay.
installed this, sir? Ayana.
Yes, exactly. So that's the major organization. That's the standard of what protocols we are currently using. But installation and all it comes when the countries and the major stakeholders of that particular country. Let's say in India we have Geo, right? So Geo in collaboration with multiple other vendors across the globe, they install it in conjunction with the government. So the government might provide some of the amount in that if they have any sort of thing which is required from these private players. Otherwise, the private players themselves install it and maintain it. But all in all, at the end of the day, it goes to a authority, right?
Yes, sir.
Okay, so this is something now. So is your doubt clear regarding MTU jumbo frame and MSS, and everybody has understood how the data packets are actually flowing,
Yes, sir.
right? What about others?
Yes.
Yes, sir.
Okay, okay. So now, right. So I think in the previous session, what have we talked? Okay. So so we started with the IP addressing concept in the previous session. Okay. So today, uh, let us discuss about a little bit more about IP rules and the classifications of IP. So in the previous session, I believe I have told you the title that the classes of IP. So A, B, C, and D and E, and the basic information about that as well, right? The ranges from where to where it actually starts and from until which particular address it ends. And then we have also discussed about the broadcast, multicast, and unicast, right? Now, one important thing about class D. So the important thing about class D is class D IPs are used for multicast purpose. This we have discussed in the previous session. You can make a note of these things of today's class. So class D is used for multicast purpose, and this multicast purpose gives an advantage to the class D IP for utilizing the same in the routing protocols. So we'll come and learn about a little bit of routing protocols in the later course, but there are routing protocols, and by routing protocols, what I mean is this. So we just discussed about sending the packet from one router to another router. How does this happen? This happens based on the routing protocols. And these routing protocols are working in layer 3 of the OSI model or the TCP IP model, right? So in the network layer is where the routing protocols actually come into picture. Now, if you see here in the IP addressing, so there are, you can make a note of these routing protocols. So there is RIP protocol, EIGRP routing protocol, right? and then we have OSPF protocol, right? Then we have border gateway protocol, that is BGP. So each and every routing protocol comes with different configurations, different requirements, right? In within the network. So if there is a big organization, let's say from within Hyderabad only, let's assume that there is an organization, and the data centers of that organization or the offices are located in multiple locations. Let's say one is in Panjagutta, one is in Kukatpalli, right, and one is in somewhere in Gachibowli. And now these offices want to communicate among each other. They do not want to rely upon internet, they do not want to rely over ISP. So they want a secure infrastructure among themselves only. So how will they do this? In simple terminology, what everybody will get an idea is we will connect them using the routers and the cables. Simple. And that's actually the right answer. But that's fine. But look at the organization's capacity and the number of users the organizations might be having. So here around 1,000 users are there. Here around 3,000 users are there, because this might be the headquarters, who knows, right? Here around 6,000 users are there. Now, for these many users, how much is this? About 10,000 users. You cannot rely on only one router at each location and only a single cable, right? So infrastructure perspective is different, but in order to route the packets, let's say there is one user sitting here, he wants to send some packet to the B user here on this organization. So they have to communicate. So this organization has this particular location has to communicate with this location. How will they do that? They will apply any one of these routing protocols, and these routing protocols, let's say we are configuring the routers using OSPF, right? OSPF routing protocol. Now, when you configure the routers with OSPF, what happens is you are informing the adjacent router that, hey, I am using this particular protocol, that is OSPF. This also will be configured by the network administrator for OSPF, and this also. Okay. Once this is done, these routers are aware that okay, everybody is into the OSPF protocol. Let us see what is the address they are hosted on. So the address will be 1.1.1.1 for this one, 1.1.1.2 for this one, 1.1.1.3. Simple. Now, in the external portions, they have connected the routers using OSPF. But what about the internal infra? So this is, there is one router here, there is one switch here, there is one router again here. So this user wants to send some packet here. How will he do? He will have to first go to the default gateway, right? From here it will go to the switch. From here it will go to another router, and so on and so forth. It will reach the external router here, right? Once it goes there, from there it will be using the OSPF protocol and going outside. But what about the internal infrastructure routing protocol? So here, because it is internal infrastructure, they might be having other routing protocol. Let's say it is RIP, right? Or they might be using EIGRP. EIGRP is little bit complex to configure, but that's okay. So it could be that, but generally RIP version 2 is sometimes used. In general terminology, it is used. And now you might be getting a doubt, at home we do not do this. Why is it required that an organization is wanting to do this? So in your home routers, they come inbuilt with the basic configuration. So it is nothing but what you do, you just configure a router here. Your main purpose of your home router is to provide internet access over Wi-Fi network or cable, right? You are not trying to route the packets from this router to another router and so on and so forth. So what does your ISP do? He'll come at your home, he will attach the internet cable into one of your WAN port. WAN is nothing but wide access network port, right? So what he will do, he'll attach the cable into this. Now simply once he attaches this, the light on the router is green and everything is working fine. But what if you want to connect this router to another router? Now comes the concept of the routing protocols. But on home routers, there is no interface. There is no interface for you to configure the routing protocols, right? So in future sessions, once we come to the routing protocols in depth, maybe we'll check about RIP and OSPF, right? We'll configure a lab for that. We'll try to check in that. So I'll show you how that works and how these routing protocols are actually functioning, right? So the major important thing about class D, what I want you to make a note of is regarding multicasting capability of class D, right? And the routing protocols because of this multicasting capability. So multicasting capability, as I earlier told you, is nothing but from one to many, right? This is called multicasting. That is how it is working. So this router can be connected to another router also, no problem. Or it can be connected to another router, not a problem. For this particular interface, the router will be communicating over a different IP. Let's say we took 1.1.1, right? For this interface, it will be connecting over 2.2.2, right? It will be connecting here for 3.3.3, not a problem at all. One router can function communicating with multiple other locations, multiple other IPs, and it can route the packets accordingly. And that is the reason why for each data packet, we need those TCP and IP headers to be encapsulated. Otherwise, this router will get confused. This router will not understand where does the packet go because there is no default route here, right? So, so what is default route? Everybody is making notes, right? I have already told you in the beginning of the sessions that the moment we keep continuing, additional points will come up. And I want you to make note of this and ask me any doubts you have got. Or you can research at your end as well. But whatever terminologies I am trying to tell you here, these are important. Because in interview, this is what people look for. The technical terminologies, what we are using. So you cannot go ahead and tell in an interview that the data from this router is going to the other router. No, the packet or the payload is being transmitted towards the other router using so and so protocol, so and so routing protocol, something of that sort, right? So what is a default route? Default route is nothing but this, what we have just discussed. So here, if you see, I have told this router that if the IPs are 1.1.1, go only to this route, right? So this is a default route. This also is a default route. This also is a default route. But what is a no default route? What is a no default route? It's simple. The packet, let's say your organization using a no default route environment, right? So this is your router. There is another router, right? There is another router. There is another router. Nobody is aware of each other. No other router, no each other routers are aware of each other, but still the packets get routed. The packets in no default route environment are broadcasted like this or multicasted like this. It is like, okay, you also try to figure out where the packet should go. You also try to figure out, you also try to figure out. So what happens in no default route environment is you utilize a lot of resources. Utilization is high, but security is more. Security is more because if a attacker tries to hack this particular router, he or she will not understand where the packet is going, whether it is going here, 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 or if other location if it is going. He or she will not know that. But in default route environment, they will. What if the attacker gets access to this router? They are in clear, they will get to know everything. They will just download the configuration on that router simply with a very basic command, right? And once they download the configuration, they will check which particular IP is routed to which particular location, and accordingly they will initiate an attack. right? So that is the reason why it is important for us to learn first networking and then the security of that network. And to come to this point, we have to first understand the basics of networking. Okay, so I know this is a little bit complex. If anybody has idea, they might be understanding. If nobody has learned until now or not aware of this, they will get confused. But if you have doubts, ask me right away. If nobody tells anything, I'll assume that you do not have any doubts and I'll continue.
Even routers use encryption. You just told security.
Exactly, yeah. Yes, routers also use encryption. There are different standards of encryption on the router. We have WPA, right? We have AES encryptions. We have the hashing algorithms. We have MD5 hashing algorithms, right? During SSL handshake, was the encryption standard discussed?
Sir, you told about SSL, but there are many doubts for me in SSL because SSL now became TLS, right? Transport layer security. And now I have seen in the website like TLS are of versions 1.1, 1.2, 1.3. What are these, all these things?
Right? So it's nothing. It's just that the upgradation of the protocol. That's it. So in TLS 1.1, in TLS 1.2, and TLS 1.3, the difference is on speed, right? The speed at which the handshake gets established. So initially we sent a client hello packet, right? The normal scenario, client hello, and then we see the server hello, and then so on and so forth. We negotiate for the keys, and once the pre-master key is there, the same is sent back, and then we send them the normal encrypted handshake message, and we tell the connection is established. So you see how much flow is there. There are many messages here. Now, when these many messages are coming and going before you actually, let's say you're going to google.com, right? When you're going to google.com and your system is sending a client hello first, here google.com is there, right? So google.com is in United States, you are sitting in India, and client hello you're sending here, then the client hello, the server hello is coming back, then the certificates are exchanged, then the pre-master key is generated where the encrypted content is whatever content we want to encrypt, we will be sharing a pre-master key so that a key can be generated here and a key can be generated here. Once the keys are generated, the same is acknowledged back, right? And then we tell that okay, everything seems to be good, then we send an encrypted handshake message. The same thing happens with the web server also. They also send encrypted handshake message. You see how many messages are here. That utilizes this. This is of unnecessary thing. What the end user doesn't want. The end user wants content. They do not want to wait for the packets to flow. They do not want this client hello and server hello. This all nobody cares. So now you might be seeing on your mobile phones or on your laptops, you're going to google.com, immediately it is opening. Why? Because that happens based on the version 1.3 or 1.2, right? Now, another difference between these versions is this is one number one. Number two is the encryption standards, what each and every versions actually use, right? So the encryption standards, if you see the encryption standard here, there might be n number of ciphers. So when you send a client hello, along with that client hello packets, you send the cipher suite, right? So when you send this cipher suite, what happens is you're telling to the web server that I am capable of understanding these all ciphers. So cipher, what is cipher? Cipher is nothing but the uh, combination of the encryption, right? Or the hashing algorithms. So the encryption algorithms, the hashing algorithms, whatever combination is there, these two algorithms, whatever combinations this end user device can, it can contemplate or it can try to understand or maybe decrypt those things using these encryption and hashing algorithms, it will try to intimate the web server. So the web server might have hundreds of cipher suits because it's a web server, because they have support. but your system, maybe it is a very old device. Let's say you are using a laptop which is of 2000s, right? So when during like 2001, 2002, at that time the TCP IP stack was not that secure, right? If you now also, if you have an old device, go on that device and go to google.com and collect Wireshark packet captures. In that you will never see TLS 1.3 coming into picture. It will be always TLS 1.1. And the reason being, the TCP IP stack at that time didn't have these cipher suits inbuilt in them, right? So what happens is your TCP IP stack, it has the cipher suits inbuilt in them. So as a user, your device will be configured with this set of cipher suits. And as and when this Windows updates are happening, or Mac iOS updates are happening, or your mobile phones are getting updated, these cipher suits get added onto it, right? So that depends on the organization, on the vendors. Let's say the Mac OS, it's kind of secure, right? So they, on each update they add those cipher suits. Windows, it's also secure. They add those cipher suits based on the vulnerabilities what we have, because once this particular cipher suits are there, they get negotiated with the web server. So number one is speed, number two is encryption, right? So that is how these protocols actually use. And another thing is, now, okay, before that, SSL and TLS, do not get confused by these two. They both are same. The only thing is that secure socket layer was used in previous context, like 10 or 15 years back. The moment the transport layer security came into picture, the same protocol, just different variants into it, is TLS, the transport layer security. So in Wireshark, if you go in the filter section and type SSL, or if you type TLS, you get the same response. The reason being, nobody has differentiated these two. They both are same. You can, in an interview or anywhere, you can tell it is SSL or you can tell it is TLS. Nothing makes a difference here, right? So the thing what makes difference is the versions of each this transport layer security protocol what we have got. So
Sir,
1.1,
sir,
yeah,
SSL handshake are developed for HTTP or HTTPS for both.
right. It is not like that. See, SSL or TLS, what is the job of this? Why are we using this protocol in the first place? Any idea? Any guesses?
For accessing website security.
Great. So it is for security, right? Now, you tell me what is HTTP and what is HTTPS,
HTTP is not secure,
right?
and HTTP is secure, which we use TLS encryption for both sending and getting the response.
Great. So there is your answer. When HTTP is not secure, it is not using any secure protocol, there is no meaning in talking about HTTP for SSL and TLS, right? Because HTTP is not a secure protocol, not a secure protocol, because it does not use SSL or TLS for establishing the handshake, right? HTTP is raw HTTP, what you see in your Wireshark packet capture also. But in HTTPS, what happens is, let me just explain you how HTTP works. So in HTTP, initially, let's say there is a website which doesn't use this security protocols. So what does your TCP IP stack do? It does a TCP three-way handshake first. This is for sure. This why we do the three-way handshake, because these two protocols are dependent on TCP. And as I told you earlier, TCP is a reliable protocol. When it is reliable, it depends on acknowledgements. And if it is depending on acknowledgements, based on the TCP stack, the TCP will initiate the three-way handshake. That is, it will send a SYN packet, and then it will wait for a SYNAC, and then it will send an acknowledgement, and the session is established, good to go. But now you as a user are browsing a website which is not secure, let's say HTTP based website, and you're trying to go to, let's say, actually I know a very good HTTP less website is this one, example.com, right? So if you go to example.com and you give the protocol there as HTTP example.com, I think they moved to SSL, or you can use HTTP. We'll see now. I'll show you. Uh, no SSL, no SSL .org, right? So what happens is it relies completely on HTTP. So your TCP stack will first initiate a three-way handshake, right? And this three-way handshake is also not secure, right? Now, when this is a HTTP and it is not relying on the SSL or TLS, you will immediately see a GET request. What are you getting? What do you want? You want the headers of noSSL.org. So you're telling to noSSL.org, give me the information about your website. So you send a GET request, and in the Wireshark packet capture also you will see this directly. But when you are using the TLS or the secure protocol, the initial thing here also happens is the TCP three-way handshake. The second thing is the TLS or SSL handshake. And here, as I told you, initially client hello, server hello, client key exchange, server key exchange, whatever certificates are there, then the pre-master keys and all everything, and then the session gets established for TLS. The third step here is all the packets are encrypted. You will not see a GET request. You will not see the request what the end user is trying to do. So what is happening here basically is in very simple manner, you on your browser go to website google.com, and the google.com is secured by TLS or SSL. So now whenever you are trying to get the information, so if you want some information from a web server, you use the HTTP methods. So these HTTP methods are completely encrypted because of this TLS handshake. So only you and only the web server can decrypt these packets and see what actually the data is in that, right? And how does this happen? This happens because of the TLS and SSL handshake. During this handshake, this party and the web server, they both negotiate on a cipher suit, and they both negotiate on a pre-master key. This pre-master key, these all are mathematical calculations, so we need not worry about this. This is completely dealt by the cybersecurity experts, not at all required for us. But what happens is these cipher suits and the pre-master key, based on the mathematical calculations, a key is generated here and a key is generated here. And in between, whoever is the party which is taking packet captures, they will not understand anything. They will not be able to comprehend what is going on. Right now, I'll show you how this HTTP and TLS handshake is happening on a Wireshark packet capture. Just a second. This is done, right? And once this is done, you are trying to get some request. Everything is encrypted, so there will be a get packet. That's fine, but this will be encrypted within the TLS packet. So you will only see in the Wireshark packet capture as application data, but you will not see the content of that data, because you as a Wireshark, because you are capturing the packets, this end user knows what content is there in that, but you are sitting in the middle here and capturing the packets, right? On this line, on this cable, you will not understand decrypt those how to decrypt those packets, right? And only the web server knows how to decrypt the packet, because these both have the keys along with them. So the decryption and encryption packet keys they have. So that is how this HTTP and HTTPS work. So if there is something called as HTTP within your question or something, simply it is not a secure protocol. It does not negotiate a TLS or SSL handshake, right? Is this clear?
Yes, sir.
Okay. Now, I'll try to show you how that actually is happening. Just a second. Okay, instead of getting a packet there, let me mm, 1 second. Where is this? Okay, now, so we have this, we have this here. Okay, so now I'll just present my screen. Where is it? Okay, so I believe you're able to see my screen. So towards the right, if you see, you can see I have started the packet capture here. Okay, and I can see there are n number of packets which are flowing from my device to some n device or something like that. Okay, and now I am trying to go to, where shall I go? Uh, let's go to some HTTP based URL first. So 0 okay, instead of this, let's go to, let me change the protocol, then they are moved to HTTPS. Right. So I have just done example.com. Let me stop this and restart the packet capture. Let's open a new tab. Let's go to HTTP because we are trying to search for that, example.com. Okay. So what we have done here, we are trying to request for a non-secure HTTP protocol. Okay, and we are going to example.com. So I click enter. You can see here it says not secure. Why does Google tell that? Why does Edge tell that? Microsoft Edge is aware that this is a HTTP URL, so simply do not enter any sort of personal information here. Now let's stop the packet capture here and let's search for SSL. So I told you SSL is completely encrypted. So if we see SSL here, we should not be seeing any packet related to, just concentrate on server name. You should not see any packet related to example.com. See, you don't have anything for that. Or let's try to simply search for example. So it says, so here is the domain name system. What it is doing is, see, it is querying. It is sending a query request, standard query, and then we see a response back. And in response, I can see a IP here. Now this IP is where we are actually going to. Let me copy this IP and let us search that IP here. Based on that, we will see the, yeah. So here you can see, as I earlier told you, where is this? X. Let's follow this. Why didn't it capture? Let's capture it again. It didn't capture the packet. Just a second. Okay, so it captured something. Yeah. So this is what I wanted to show you. Now, if you see for get, you can see here, right, that 192.168.0.108, this is my IP address. And from which source port? This is a random source port, 63,106, and it is sending the destination port HTTP port 80, right? Port 80 is nothing but a non-secure HTTP protocol. Port 443 is secure protocol, right? So if you see here HTTP, it is trying to get. So I am sending a GET request to the web server, and what am I trying to get here? Let's expand the HTTP. So you can see, literally I can see everything here. Like I want example.com, right? And the user agent, what I am currently using, user agent is nothing but the browser what I am using. So you can see here it is telling edge 124.0.0.0, which means that I am using 124 version of edge, right? And it is just asking for the data. Now, if I click on the information what this web server shared, you can see the source changed here, 93.184.215.14. This is the web server sending the response back to me. If I click on this, whatever data they shared over the screen, if you see on the screen, you will be able to see it here. So you see here that there are headers for each and everything, and then we see the content length, what we have got, and the content in it. So the request URL, the data, the file data, how many bytes of data it is carrying, everything we have in this. But uh, right. So this HTTP header is carrying this data here. Now, whatever data you see here, if you see the line-based data which is in text or HTML, the document HTML type and all, if you just copy all of this, maybe just a second. What did it copy? See, you see this? I just copied whatever data was there in that. In that, let's remove the line here. So what I'm trying to show here is if HTTP is insecure, if it is not secure, then what can an attacker do? Why you should not use HTTP based URLs? So you see that I have the data here. I captured the data. Whatever data I have, I captured it because I am the man in the middle running Wireshark here. I tried to go to a non-secure website and I captured this, right? Now from here I can see that I have got the content here, but I don't know how to comprehend this. It's simple. It's an HTML based content here. What we do is we will save this file. We will save this file on our downloads folder, and we will mention the file name as test.html. Okay. Now once I save this file, and just a second. Uh, right. So you see test.html file here created. If I double click on this, let's open with Edge. Once you open, you see example domain. This domain is for illustrative. You may use this domain in literature without prior. And if you see this example domain here, where is the tab? See, you can see the thing here, example domain, and what data I have got here. So an attacker, if they get information, they capture the details, they can get the bits and bytes of pieces what you are trying to configure there. Let's say you go to an insecure website like this and enter your email ID or password, you enter your credit card details, and then you enter your CVV number of your card, and then you enter the password. Immediately, because it is insecure, automatically we will be getting all the information if somebody is capturing. Let's say you are in a hotel, or you are in some cafe and you are using their Wi-Fi. There, if they are running a packet capture like this and you are being sent to a non-secure protocol, automatically your details are being visible to others. No matter what you do, no matter if you are sending a message to your friend, if you're trying to do some sort of video call or something, everything can literally be reassembled back, right? So this is how it actually works. Okay, this directory, you can see this is coming from my own downloads folder, and this is something which I visited online. From the Wireshark packet capture, I have gathered the HTML code, and this HTML code I have created the .html file, and based on that I can see the content. Is that clear? Hello?
Yes, sir.
Yes.
Any doubts in this? Any query? Now, since we have seen example.com as a non-secure URL and we are able to see the details here, what I will now do is I'll start the packet capture again, but this time I will keep the HTTP, not HTTP, let's say SSL. Okay, and in this I will create a secure protocol, HTTPS, right, and I hit enter. Once I do this, you can see the browser is now secure. I can see connection is secure here. That's good. And now I stop the packet capture. Let's search for that. You can see here the client hello. If I try to stream this packet now, I'll show you what content you can see. You cannot see anything, literally. You see the IP remains the same because that's the web server's IP. But as I told you earlier, you can see here the TCP, right? And then you see the client hello. In client hello, you are trying to tell to the web server that I want to connect to this SNI, example.com. Because on the same IP, there can be hundreds of URLs that can be configured. So that is the reason why we use this particular data here. I'll show you in the client hello. And I also told you in the client hello, we share the cipher suits which are supported. So you can see the cipher suits here. See, I told you the advanced encryption system and the hashing algorithms. So this is the encryption algorithm and this is the hashing algorithm. GCMSHA 256. So 256, that's the standard of that particular hashing algorithm, and AES 128 is the standard of the encryption algorithm. Similarly, there are many such encryption and hashing algorithm, RSA, ECDHE. So these are the key making protocols based on which the sessions are negotiated, right? Now, if you see the client hello here, we send the request here and you can see the SNI signature. Yeah, not on this. Yeah, server name. So this is called as server name indication extension. So here we are trying to check we are telling the server that I am trying to connect with you for example.com, right? Now post this, the next message is change cipher spec and client hello. Okay, this is coming back again. Now you see the server hello. In server hello, what is happening is the next message, it is telling, okay, fine, I will choose one of the cipher suits and this is the cipher suit. See what it chose. From whatever client hello, there was a cipher suit here. It chose this cipher suit. The ID is 1302. Let's see, 1302. So it chose this particular cipher suit. So from 16 cipher suits, The web server chose 1302 as the cipher source, and it is telling that it is supporting TLS 1.3, right? It is negotiating on TLS 1.3 support, and so on and so forth. It is just giving the information, but it is also telling that the application data protocol is hypertext transfer protocol, that is our HTTP, right? So it is just informing that okay, there will be a HTTP application what you'll get. Once that is done, you can see all the packets are application data and everything is TLS. There is no HTTP protocol here. And if you see, let's say this application data, if you click on it, if you click on it, you will see what data is in that, but you will not see the data actual. See, you can see encrypted application data. Now, who can decipher this? Nobody. Only the web server can decipher it, and only you can decipher it because you have the key. And as I earlier told you, the difference between TLS 1.1, 1.2, and 1.3 is the exchange of the packets and the speed at which they negotiate the keys. So here in 1.3, you can see there is a simple client hello, right? And then there is a chain cipher spec client hello, and then server hello and application data. There is no utilization of multiple packet exchanges. So within three packets, literally your session got negotiated and it got started. So how much was the round trip timer for this? If you see the round trip timer, the max round trip timer for this was 0.25120400 milliseconds. Very minute time, 25 milliseconds. Very, very minute. So 0.25, not 25 milliseconds also, it is 0.25 milliseconds. So within a fraction of seconds, these all packets got negotiated, right? Now, post this, application data is flowing, which is encrypted, and you are unable to see how we were able to see in the HTTP based. So that's the difference of this. Now, this is the packet capture for TLS 1.3. I cannot replicate based on TLS 1.1 and 1.2 from my device, but what I can do basically is we can look for packet captures online. Uh, let's see just a minute. Okay. Just this is using TLS 1. Okay, fancy protocol. No, 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 this will confuse you. Second, second. Okay. Okay, so there are some recaps. Let's see. There's MQP, MySQL, capture later keylog of necessary get request over. Okay. clear packet captures. Just a minute. Okay. HTTP, HTTP 2.0, HTTP 3. Okay, so I think we have TLS 1213. I think they do not have TLS 1.1. However, I think this should show us AES. Right. So, okay, they have replicated this in a lab environment. That is why you can see the loopback address. I told you about loopback address earlier. The reason why we use it to test our own infra or our own devices if they are functioning properly or not. You can see this loopback address destination, source and destination are same, but the source port and destination ports are different. So what this particular user or this particular person might have done is they might have configured an application which is hosted on this particular destination IP and the port 443 from their local machine, which is randomly choosing a port here. It is sending the client hello packet to this particular destination. So they must be testing some or the other protocol or the ciphers. That is the reason why they have done. So you can see the clear thing here. 1, 2, 3, 4. So literally after 4 packets, you are able to see 1, 2, 3, 4 application data. So this means that it took around 4 exchanges for the TLS 1.2 protocol to get initiated for sending the application data. But in our previous PCAP for TLS 1.3, we saw only literally 3 packets and done. It came to application data. So, so that is how, based on these versions, they are changing things. They are changing the encryption algorithms, right? They are trying to increase they are trying to reduce the time for which the users get the access. So that is how actually it works. I believe TLS 1.1 packet captures are not available. However, I think some URLs still use TLS 1.1. I'll see if I can find that. I'll show you. But in TLS 1.1, it is the same flow. What you'll see, client hello, and then you will see server hello. Then you will see the pre-master key, and there will be more two messages here. From that, after that, you will see the chain cipherspec message for client hello. I mean for the client, and the same message chain cipherspec message will come from the server as well. What does this chain cipherspec message mean? It indicates that to the destination and to the source, each other they it's like an acknowledgement to each other, telling that now the job is done of encryption. I can encrypt and decrypt the packets. Can you do that? So if there is a chain cipherspec message coming from the destination also, it is confirmed. Okay, then that's okay. Here you can see the chain cipherspec is coming in the third packet itself from the source. So this means that just within 2 messages, the third message, before third message only, the source configured a key, right? And it sent an encrypted handshake message. Now, once this encrypted handshake message received by the web server, in our scenario, it is this particular port. Once it is received by the web server, it is trying to decrypt that, and then it is telling chain cipherspec, and then it sends the same encrypted handshake message back so that it can be decrypted. Yeah, right? And once that is done, it's simple that they start sending the application data. So that's how it is working in TLS 1.1, 1.2, 1.3. The process is simple. You just have to understand what happens when. So that basic flow, that is client hello, server hello, client key exchange, generation of the pre-master key. So that is something which you all we must be aware of. But the versions differ, and the security protocols, the speed at which it initiates that particular negotiation, so that all changes. So that's about that packet capture. Now, what other doubts do we have apart from TLS SSL? Okay. So today, from IP we went to TLS and SSL. Okay. Okay. I think even we have crossed the time. No problem. We'll continue tomorrow for the IP addressing part, and post that we will most probably jump into the subnetting part, what subnetting is and how it is and all. Then we will see the next thing what is to be done. Could be routing protocol, or we could jump to the layer 2 protocol and then come to the routing protocol. We'll see. So is it clear? Is everything clear from today's?
Everything clear, sir.
Okay. You
And
can
after subnetting, you can tell about Ethernet header, right, sir?
Ethernet header is nothing. There is nothing much in that.
Okay.
Yeah, so it's just a basic protocol what your cable generally uses. We'll come to Ethernet header as well. We will try to discuss about cables, the categories of cables, right? There are different categories of cables, category A, category B, and then how these LAN cables are actually connected with each other, right? So there are different types of cablings as well. So once we go there, we will try to discuss that. But that is something related to hardware components of your networking devices. So in cable, we have different things, the categories of the cables, and based on that, we have the combinations of each and every wire. According to that combination, the speed of each and every cable differs. So some of you might have 1 GB per second link at home. So that cable is different altogether. Some of you might only have 100 MB per second cable. That cable is different, right? We will discuss about that. Not a problem. Okay, so
Sure, sir.
are
Thank you.
we, are we good to end the call, or we still have any doubts? Any further doubts?
My doubts are clear, sir. Thank you.
Yep. Thank you. No worries. Okay then, team. Have a nice day. We'll meet tomorrow. Bye.